All right, hello class. Um, uh, Good afternoon. I realized that I totally goofed with your final exam quote. Uh, in that I had intended for you to do it this week, but I think I assigned it last week. So, but anyways, it's not due until this Wednesday. I goofed. Um, hey, Michael, I'm glad you're caught up. Um, So, at any rate, I won't be grading the final exams until this Wednesday. Um, so, all right. I wanted to show you my latest knife that I'm working on. This is a dagger, and I'll tell you what. This one is significantly sharper than my last one. You can look at the edge there. Edge looks pretty good. This one is like almost dangerously sharp. So I think in order to make it truly sharp, the knife has to be fairly narrow, or it has to be like the edge has to be really tapered. And so I'm pretty close to that here. I'm probably gonna grind away some more of the, you basically I have like a millstone and I like grind away um, the metal, and so I'm trying to get it down to the point where it's thin, pretty thin, and it can really be sharp, like razor sharp. Like I want to be able to shave with this, and but it's already sharp enough where I just took it and there's like a tree in my backyard, and I was just like and it stuck in the tree, so it was pretty cool. Um, so, anyways, this is what I'm working on. I'm also trying to put a guard on it. Um, you know, so I need to like kind of fold. I want to fold these out on either side, and then wrap them around so it has kind of like a curly guard. And then I want to make this part more spherical. So, anyways, I'm pretty happy with this one. Um, okay. So, today is sort of our last day of talking about how to determine distances in astronomy. Okay. So, I wanted to talk about three other methods of determining distance, and only one of them I'm going to ask you to actually know how to do the calculations. So the title of this lesson is Other Methods of Determining Stellar Distances. So how far away is the star from Earth? Okay? So um, the first method I want to talk about is what is called a Cepheid variable star. Okay, so there are stars out there, okay, that have a brightness. If we look at the luminosity of the star as a function of time, the luminosity as a function of time varies. This is not the same thing as the twinkling of the star, okay? The apparent twinkling of stars is caused by the Earth's atmosphere, okay? It's not a real brightening and dimming of the star. If you were out in outer space, you wouldn't see stars twinkling. But there are stars that the brightness of the star gradually changes over time. So this isn't like multiple times per second. I'm talking about this brightness change the period of the brightness change could be 40 days or something. Okay, so there's very gradual change in brightness. Now we understand why this happens. It has to do with basically. I haven't really talked about stellar physics yet, but basically it has to do with chemical changes in the atmosphere of the star. There's basically like periodic chemical changes that cause the brightness to change. Okay? And from what we know about the physics of these Cepheid variable stars, there is a correlation between the period of the changes in brightness and the average luminosity of the star. Okay, so the average luminosity would be this, right? The value that it wiggles around. And so what we find is that basically that there's a, some relationship. It's not a linear relationship. I don't know what it looks like exactly, but I know that as the period gets longer, the average brightness of the star luminosity of the star goes up. Okay? So basically what we do, if we want to know how far away that star is, and it's a Cepheid variable star, what we do is we watch it over a period of 40 days or whatever and determine what is the period of the fluctuations in luminosity of the star. And then we go to this graph and we say, the period is this, so its luminosity, its average luminosity must be that. And then we have our formula for apparent brightness equals luminosity over 4 pi d squared. So we got the luminosity from the period of the luminosity fluctuations, and then we get this, the apparent brightness, from a telescope. Okay, and you can see that if we know B and we know L, we can calculate the distance. Okay, so that is using Cepheid variables. Okay, it's a special type of star. So not every star works like this. It's only certain types of stars. But maybe we see a cluster of stars. We see stars that are obviously grouped together, and we don't know how far away the cluster is, but maybe one of them is a Cepheid variable, and so we could determine the distance to the Cepheid variable, and then we say, well, they're all clustered together, so they're all approximately this far away. Okay, so that works pretty well. There's another method, and the other method is to use type 1a supernovas. Supernovae, that's the plural of supernova. So a supernova is when a star explodes, and I'm going to talk about stellar physics actually in my next lecture, I think, but basically it is when a star explodes, and there are multiple reasons that a star could explode, and type 1a is a special type of supernova. So there's like type 1a, type 1b, type 1c, there's type 2, and type 1a supernova is basically when you have a binary star system. You have a big star orbit and a little star orbiting around each other. Okay, so they kind of do a dance, orbiting around each other. And what happens is, as they're orbiting, gas from the big star will start to spiral on top of the little star. Okay? And it turns out that, again, from our understanding of the physics of stars, once enough gas from the big star falls onto the little star actually explodes. That's called the Type 1a supernova. It explodes, and when it explodes, it completely destroys the big star. And and so what is observed is that Type 1a supernovae, they have an extremely consistent luminosity. So basically, there's only minor differences between Type 1a supernovas, okay? So they all have the same luminosity. They all have the same brightness, okay? So again, we go to this formula. Apparent brightness equals L over 4 pi d squared, okay? All right. And the apparent brightness, again, comes from the telescope. Okay. The luminosity comes from the fact that it is a Type 1a supernova. And all Type 1a supernovas have more or less the same luminosity. And so we can solve for D. Okay? So that is a common method of determining stellar distances as well. Okay? These two methods, they're often called, these two events, Cepheid variable stars and Type 1a supernovas, these are often called standard candles. Okay? Candles meaning a source of light. Standard meaning that they're consistent. Okay? Cepheid variables are consistently have this relationship between luminosity and period of brightness flickering. Okay? Type 1a supernova, it's consistent, okay, for all Type 1a supernovas. So those are two methods using standard candles. Okay? The third one I want to talk about, and this is the last one that we'll learn about, is called Hubble's method. Okay? And this method works for basically entire galaxies that are extremely far away. Okay? We are talking about millions of parsecs, megaparsecs. We're talking about billions of parsecs, gigaparsecs. These distances are so great that, the size of the entire galaxy, the galaxy is so far away that through a telescope, it is basically just a point of light, okay? So you have no chance of viewing individual stars in the galaxy, okay? It's so far away that we're just looking at an entire galaxy, okay? So this is called Hubble's method, okay? And so I'm going to direct you to the image that I have inset, okay? And basically what this image shows is that, so each of these points on the graph represents a galaxy, okay? And we were able to measure the distance of the galaxy from the galaxy using some method like a standard candle or spectroscopic, the other methods that we've learned about, okay? Parallax, or the other method, which I didn't give you the name of, but it's called spectroscopic parallax, or Cepheid variables, or type 1a supernova. So we were able to determine the distance to all of these galaxies using the other methods that I've already taught you. Okay, so Hubble did this, and what he decided to do was graph the velocity of the galaxy versus, so how fast is the galaxy moving away from us, versus the distance that the galaxy is away from us. Okay, so this is the velocity of the galaxy away from us. Okay, now how do we know how fast a galaxy is moving? We use the Doppler effect. Okay, so the Doppler effect, and I'll talk more about that in just a moment, but we have a method of determining how far away a galaxy is moving from us. Okay, and what Hubble found was that there is a correlation between how far away a galaxy is from us and how fast it is moving away from us. And basically what this correlation shows is that galaxies that are farther away are moving away faster. That's the meaning of the positive slope. Okay, galaxies that are farther away are moving away faster. Okay, so why is that? Why is that? And the reason is that space, the universe itself, is expanding. Okay? Michael, I'm going to get to your question in a second. Space is expanding. Okay? So why would something that is further away be moving away faster? Okay? Space itself is expanding. All right? If there is... Hi, Ivan. Hi, Ivan. Hi, Ivan. Hi. Hi. Hi, kitty. Kitty meow meow. I capture you? So space itself is expanding. If there is twice as much space between you and me, then there's twice as much space expanding. So you're going to have twice the speed away. All right? So the more space there is between you and a distant object, the more space there is expanding, which means that there's a greater speed that it's moving away from you. Okay? All right. Now, why is there so much scatter in the graph? Look at the graph that I have on the screen. It has a ton of scatter. When I say scatter, I mean it doesn't lie perfectly on the line. It's all over the place. Okay? Why is that? Well, it's because even though space is expanding, galaxies still have their own velocities. Okay? Galaxies still have their own velocities. So basically the speed that we see the galaxy going away from us is the sum of two speeds. There's the speed of the space expanding, and then the speed of the galaxy moving through space. So we have to add those two speeds together to get. And so there's some scatter in the data because of that. All right. So this is pretty cool. Notice how galaxies are moving really fast, okay? Look at the scale on the vertical axis. It's thousands of meters per second. So some of the galaxies here are moving away at 5,000 kilometers per second. So galaxies are not moving slowly. They're moving really fast. And then also look at the distance between galaxies. Galaxies are, so remember, the distance between stars, maybe I should talk about this, okay? The distance between planets is approximately AU, all right, astronomical units. The distance between stars is approximately light years. The distance across a galaxy, now a galaxy is just a gravitationally bound collection of stars, is going to be roughly 10,000 light years. Okay? But the distance between galaxies is of the order of millions of light years plus billions of light years more. Okay? So, once you talk about between galaxies, it becomes more and more difficult to look at individual stars, and we just kind of look at the galaxy as a whole. All right, so because this is a linear relationship, okay, it's actually a proportional relationship, we have what is called Hubble's law. Okay? Hubble's law. And Hubble's law says that the velocity that a galaxy is moving away from us is equal to h, which is a constant called the Hubble constant, times its distance away from us. Okay? The value of the Hubble constant is 68 kilometers per second per megaparsec. So per millions of parsecs. Remember, a parsec is, 1 parsec is 3.3 light years. All right? So that's Hubble's law. So what that means is that if a galaxy is 1 megaparsec away, 1 million parsecs away, we could expect that galaxy to be receding from us at a speed of 68 kilometers per second. If the galaxy is 2 megaparsecs away, we would expect it to be receding at 136 kilometers per second, times 2. If a galaxy is 3 megaparsecs away, we would expect it to be receding at, what would that be? 204 kilometers per second. Okay? So the farther away it is, the faster the galaxy is receding. On to another question, which is, how do we determine the velocity? Okay? How do we determine the velocity of a galaxy? And we use the Doppler effect. Okay? The Doppler effect. All right? So what we do is, if we look at, say, brightness versus frequency, we might see a spike. Okay, remember when I was talking about how hydrogen, for example, hydrogen has certain electron energy levels, and when electrons jump between energy levels, it emits light of a very specific frequency. Okay, so there's a certain frequency that, for example, hydrogen emits. So this is the emitted frequency. Okay, but because the galaxy is moving away from us, the frequency that we receive is Doppler shifted. Okay, so if a source of light is moving away from us, the observed frequency is going to be lower. So this is the observed frequency. Okay, and so there's a certain amount of frequency shift, which I'll call delta F, and this is called the redshift. Why is it called redshift? Because the galaxies are moving away from us, the frequency is lower, and red is on the low frequency part of the visible spectrum. So something that is emitting yellow light might appear red to our telescopes because it is moving away from us. So the frequency of the light is shifted lower. Okay? And so there's a nice little formula from the theory of the Doppler effect, which says that the shift in frequency divided by the frequency that is emitted is equal to the speed divided by the speed of light. Okay? So basically, we look at a particular spectral line that we know about. So for example, hydrogen. We know all about hydrogen. We know what frequencies hydrogen emits. We look at our galaxy and we see that we're not getting the right frequencies for hydrogen. There's a shift. Okay? And you can be extra certain because every frequency of hydrogen is going to be shifted. Every frequency is off from hydrogen. So we're able to get multiple checks of how fast the galaxy is going because we have multiple elements, multiple lines from each element, and we can be pretty certain of how fast the galaxy is moving away from us. Okay, we calculate the speed of the galaxy based on this. Okay, we plug that into Hubble's law, and we solve for D. All right, so that's how it works. I'm going to answer Michael's question, then we'll do an example. Michael Judson says, since stars are thousands of light years away, thousands of light years away would be a star that is like on the other side of the galaxy from us. The closest star to us besides the sun is Proxima Centauri. It's 4 light years away. So since stars are thousands of light years away, that star could be dead and we wouldn't know for thousands of years. A friend in college said that's not the case. Why? Well, I think, yeah, we wouldn't know that a star is dead for thousands of years, okay? In my next lecture, I'm going to talk about stellar physics, and stars do have a predictable life cycle, just like humans do. We could look at a really, really old and sick human, and we could say that, you don't know exactly when that human is going to pass, but you could say that it's close to passing. The human is close to passing, right? Same thing with stars. We can look at a star, and it has certain signs that it's towards the end of its life, okay? And so we could look at a star that's thousands of light years away, and we could say this star has roughly 1 million years left before it dies. So, we can say that, or maybe we could say it's 1,000 years left until it dies. And if it's 1,000 light years away, we could infer that that star is probably not there anymore. So I hope that answers your question. So I actually disagree with your friend in college. I don't know. I would need more detail. But there is variability because you can't predict it exactly. And also, what does it even mean for a star to be dead? So I'm going to flip that question around back on you, and I'm going to say, what does it mean for a star to be dead? Okay. I mean, I have my own thought on that, but I'm curious what your thought is. All right, so let's do an example. Let's say hydrogen emits photons of frequency equal to 7.9 times 10 to the 15th hertz. Okay? The observed frequency of the photons is maybe 7.1 times 10 to the 15th hertz. Okay? I should say the observed frequency of photons from some galaxy is 7.1 times 10. So see how the frequency, the observed frequency of the photons is going to be less than the emitted frequency, okay? Because of the relative motion between us and the galaxy. Okay, so what I want to know is how far away is the galaxy? What I'm going to do first is I'm going to use this delta F over F equals V over C. So what was the shift in frequency? The shift in frequency was 0.8 times 10 to the 15th hertz. And the emitted frequency was 7.9 times 10 to the 15th hertz. And then that equals V over C, which is 3 times 10 to the 5th kilometers per second. So notice how I'm putting the speed of light in kilometers per second because Hubble's constant is in kilometers per second. All right. So this says that the velocity of that galaxy is 0.8 times 10 to the 15th divided by, let's see, 0.8 divided by 7.9 times 3 times 10 to the 5th. So the velocity of this galaxy is 3 times 10 to the 4th kilometers per second. That's the velocity of recession of that galaxy. Okay? So then I go to Hubble's law. Okay? V equals HD. And so the velocity of recession is 3 times 10 to the 4th kilometers per second. And that equals Hubble constant, 68 kilometers per second per megaparsec times distance. And notice how it's per megaparsec, so the distance is going to come out in megaparsecs. Ooh, the light is really nice right now. The post-rain light. So this says that D is equal to 3 divided by 68 446 million parsecs away. So that's basically a billion light years. We can see galaxies that are billions of light years away. Okay? So I think that's pretty cool. It's incredible. If that means that a beam of light, if we were watching light go from point A to point B between those galaxies, it would take, a significant fraction of the age of the universe. Okay? So think about that. Let's see what Michael Judson said. He said, indubitably, that makes sense. I will investigate. I think they probably meant a supernova. So tomorrow I'll talk about the life cycle of a star. And supernova is one of the ways that a star can die. I would say that a star dies when it stops having, it stops performing nuclear fusion in its core. Okay, because nuclear fusion is what causes the light from the star. So if you stop having fusion happening in the core of the star, then you are going to, then it's not really a star anymore. Okay, or it's not a live star. All right, so I will talk to you tomorrow. We'll talk about the life cycle of stars, and I hope you have a great afternoon. Bye now.